This Fluids webinar brought to you by Leeds Institute for Fluid Dynamics, DAMTP and CUP. Just a couple of bookkeeping things. The meeting is being recorded, so if you don't want to appear on the CUP website, then please keep yourself your cameras off. So it's my great pleasure to welcome Jacques Vanneste from Edinburgh University to give this webinar. Jacques is an expert in geophysical fluid dynamics. In particular, he's interested in dynamics on two timescales, wave mean flow interactions, mixing, lots of very interesting problems in GFD. Of particular interest, he's interested in all types of waves, such as inertial waves. He's the winner of the 2010 Adams Prize and is a Fellow of the Royal Society of Edinburgh. And today he's going to talk to us about the generalised Lagrangian mean, how to formulate it, and also how to compute it. So over to you, Jacques.
Thank you, Steve, and well, thank you for the invitation. So my aim today is to sort of popularize a little bit generalised Lagrangian mean, GLM, and I'll do this in two parts. One will be about the formulation, try to make it accessible by introducing a bit of geometry. And the second part is about the numerical computation of Lagrangian mean. This is joint work with a bunch of people. Andrew Gilbert collaborated with me on the formulation part, and then Hossein Kafiabad, Abhijit Means, and Lois Baker on the computation part. And I should say also, feel free to interrupt me if something is unclear or mysterious. All right, so a bit of motivation. As we know, fluid dynamics is complicated, hence interesting, partly because it's nonlinear. And as a result, it's multi-scale, typically both in time and space. And we know this very well because of turbulence. It's also the case in the presence of waves, which tend to be, in many setups, fast waves or short waves. And so we have to deal with both the scale of the flow and the scale of the waves. And just as an illustration of this, I like to show this picture, which shows the trajectory of drifters in the Atlantic, which have been dropped by Eric Dazzaro and his team quite a while ago after a storm has passed. And you see those trajectories are made up of two components. One is a slow drift with the currents in the ocean, and then there are those fast oscillations leading to a sort of helical-like trajectories. And so that's an example of a two-time scale system, right, where there's a slow time scale governing the drift and a fast time scale governing the fast oscillations, which are here inertial waves. Okay, so because of this multi-scale, we are always led to do some kind of averaging, whether we want it or not. So in numerical models, models have a finite grid size and finite time step, and so we cannot resolve all the scales, so we have to solve equations which are coarse-grained in some way, so which are averaged equations. What this leads to is a problem in which there are subgrid scale effects, which need then to be parameterized in some form, right? So the idea is that we resolve what is above the grid size, and what is below the grid size is dealt with by some representation, some closure. We also like to average when we think about conceptual models. We separate typically mean flows from fluctuations, and we have separate models for the two, and then models for their interaction. So the question here is, what is the best way of averaging a fluid system? And my focus really is on situations which are at high Reynolds number, where what dominates the dynamics is really inertia. Okay, so advection-dominated flows. And then the argument is that Lagrangian averaging is a good way of handling these flows. So just to remind you about averaging, the standard average is the Eulerian average. So for the moment, I'll be denoting my average by a bracket throughout. And we should think at the moment of this average as some kind of ensemble average. Okay. In practice, it will be a time average. It could be a spatial average, but it's easier to think of an ensemble average, so it commutes with everything. So Eulerian averaging is carried out at fixed spatial position, right? So you pick a position in the fluid, you look at what's happening at that very position, you average over ensemble or maybe over time. Okay, so you define the Eulerian average as this average at fixed location. Now we want to see what the effect of averaging is on transported fields on advection. So the simplest case is a transported scalar, obeying this transport equation, right? Transport with a velocity u. When you average the whole equation, what you get is the time derivative of the Eulerian mean, and then the mean of the advective term, which, because of it's a nonlinear term, doesn't average very easily, right? So what you have to do is to separate the field into a mean and a perturbation with zero mean. Do the same for the velocity, so there's an Eulerian mean velocity, a certain fluctuation, perturbation. You put that into your equation, you leave the average term, the kind of average advection of the average field on the left-hand side, and you move the rest on the right-hand side. This is what we call Reynolds stresses, or something similar. Reynolds stresses would be for momentum, sometimes also eddy stress terms. This is something which depends on the fluctuation, something which you have to parameterize, right? So the lesson here is that under Eulerian average, transport, in this case of a scalar, doesn't behave terribly well, in the sense that it leaves you with some stress terms which need to be represented in some way. Now, the alternative is to do some Lagrangian averaging. So this will take a bit of notation to introduce. So what I'll be using extensively in the talk is a flow map, right? So we tend to forget maybe about this, but the most fundamental object in fluid dynamics is really a flow map, which tells you where each particle goes at time t. So this flow map phi takes a particle label, which could be the initial position of the particles, and then maps that to the position of the particle labeled by A at time x, right? So you have, the picture is here, so there's a label space, it could be initial condition, you pick a particle by deciding of a label, you watch where it goes at time t, at some location in physical space. So this is my phi, and then the velocity is a time derivative of this phi, telling you about the change in the position. And just, I mean, a kind of obvious reminder, the velocity is an Eulerian object in the sense that we refer it to the current position of the particle, right? So you take the time derivative of the flow map that gives you, of a given particle A, that gives you the velocity of the particle at the location of the particle at time t, right? So this is best written maybe in this form, where you kind of highlight the fact that there's a composition involved. When you have the velocity, you have to look at the velocity of a given, at the location of a given particle. Okay, so that's my notation, which is fairly standard. Now, with this notation, what is the Lagrangian averaging? So first, let me define the kind of simplest, most naive Lagrangian averaging, which is that you average at fixed label. So you pick your particle, you follow it with the flow map, you look at the scalar field at the current position of that particular particle, and you average, right? So it's an averaging following trajectories. Now, the beauty of this is that if we apply it to a scalar which is transported, so this is the usual transport equation as shown before, what this is saying, this equation is saying is that the time derivative of the function composed with the flow map is zero, right? This is material transport. So when we average this equation, because what we are averaging in the Lagrangian sense is precisely this composition of the function with the flow map, we end up with the trivial result that the Lagrangian mean of the scalar is equal to zero, right? The Lagrangian mean of the function is an invariant. Okay, so that's simple, but also very complicated in the sense that the complexity is hidden in the flow map, right? In particular, if the flow is a bit interesting, it's going to be chaotic. The flow map is going to be stretching and folding. We can't possibly use the flow map to say something meaningful about the current state of the fluid. So then the sort of intermediate way of doing averaging is doing a generalized Lagrangian mean, GLM, where the idea is that you really do this Lagrangian average, but rather than referring the average to the label of the particle, you refer it to some mean position of the particle. Okay, so I'm going to define a mean flow map, and at the moment I'm not going to be very precise about what it is. It's some kind of flow map which represents well all the realizations in an ensemble, so where all the endpoint of a given particle in the ensemble, or if you think about the time average, is some kind of good representation of where a given particle lands at nearby times. Okay, I'm going to use this slightly esoteric double bar notation just to emphasize the fact, and I'll discuss this a bit later, that this is not really a mean of anything. Okay, it's some kind of, it's not an average of anything. It's been defined very separately from any averaging operator that may exist. Okay, and then what you do is that, just as before, you take the Lagrangian average of your function, so you average as fixed label, you average following a trajectory, but then you refer the Lagrangian mean not to the label, but to the mean position. Okay, so it's going to be a function of this mean map applied to the label, so a function of the mean position. Now, what you get for a transported scalar, if you apply this GLM average to the transport equation, is that you're going to get a pure transport equation, so no Reynolds stress-like terms, and the transport will be with this Lagrangian mean velocity. And here, the Lagrangian mean velocity is just defined as being the velocity of the mean map. Okay, so it's not the mean of the velocity in some direct sense. Okay, so the picture is this, right? So I'm imagining that I have an ensemble of flow maps. And here my ensemble is just made up of 3 flow maps. So a given particle is mapped at 3 different locations. And the idea of GLM is to represent those 3 locations as a composition where you first map the particle label to the mean position with the flow, the mean map, so this phi double bar. And then from there, there's a perturbation map which takes you to the actual position of the particles. And the notation for this is this big psi. Okay, so this is the kind of key equation of GLM, if you like, is decomposing the flow map into perturbation composed with the mean map. And everything will work provided that this mean map is well chosen, and well chosen means that the perturbation maps are somehow small. I mean, small here means close to the identity, right? So that you don't have a long way to go from the mean position to the actual position of the particle. Okay, so I said we pick the mean map in some way. What I want to stress is the fact that there is no obvious way of defining a mean map. A mean map is really a nonlinear object, right? And it doesn't add in any natural way. Averaging is really about addition, so it's really a linear operation. So there is no kind of canonical way of defining a mean map given an ensemble of maps. So that, however, I mean, several ways have been used. The first, the most standard, is the GLM approach of Andrews and McIntyre in pretty much most people since then, which is to do a component-wise average of the mean map. So you pick your favorite coordinate system, you write the mean map in those coordinates. Each coordinate is a scalar. Now a scalar is a linear object. You can add scalars, so you can define the mean of this. Okay, so that's the obvious thing to do. Certainly the obvious thing to do in Euclidean space when using Cartesian coordinates. The way this is presented typically is slightly different from what I've been doing here. The way it's presented is by saying that this perturbation map, at least its coordinates, are made up of the identity plus a small perturbation, and then we require this perturbation to have 0 mean. Okay, so these are 2 equivalent statements. One thing about this is that it's completely coordinate dependent unless you are in Euclidean space where you can think of positions as vectors, right? But in general, you cannot. And so that leads to some problems. For instance, if you do this kind of averaging on a sphere, if you have flow maps on the sphere, you average them, you find that the result doesn't stay on the sphere. So you can have the map of a part, the image of a particle ends up being of the sphere, inside the sphere, outside the sphere. So that's one thing you can avoid by maybe using better coordinates than Cartesian coordinates. What you cannot avoid is this divergence effect, which is a slightly curious phenomenon that if you have an incompressible flow, so the divergence of the velocity field is 0, the Lagrangian mean velocity that you get, so the time derivative of this mean map, is not divergent free. Okay, so there's a slightly disturbing effect, which comes largely from the fact that we use coordinates to define this mean map. And so we don't have a kind of purely geometric object, and we lose this property of being volume preserving or divergent free. There's an alternative which dates back to a work by Soward, which predates Andrews and McIntyre, which is the GLM, little GLM. Okay, so the acronym is quite annoying, but this is what it is. I won't go into much detail about this, but what you do is that you think of this perturbation map here, you think of it as being obtained by solving for the particle position of a kind of fictitious vector field. Okay, so you can imagine that the map is obtained by integrating a vector field for time 1, and now you impose that the mean of this vector field be 0. Okay, this is a completely geometric operation, unlike the big GLM. In particular, you can ensure relatively easily, simply by enforcing that this Q has no divergence, you can ensure that the Lagrangian mean that you get has no divergence. Okay, so it's quite neat, conceptually at least. The problem is that it's a very implicit definition, which you can really not work out except perturbatively, as far as I know anyway. And then Andrew Gilbert and I have also been proposing some kind of other alternatives. I mean, one is to take the GLM mean map and then just project it on volume-preserving maps. Okay, there's one way of projecting any map onto volume-preserving maps. This is the idea of polar factorization, optimal transport. So you can think of doing this. Another way is to define a mean map as a mean, the Gaussian mean. So this is a mean in a space with a Riemannian structure. Flow maps are diffeomorphism. You can think about distances between diffeomorphisms, something which is fundamental to the work by Arnold and other, the kind of geometry of the Euler equations. So there's a distance between flow map, and then you can say, okay, I'll take my mean map to be the kind of least square approximation to all those maps. Okay, so you find the map which is the closest in a least square sense using the metric on the space of flow maps. Okay, so again, I mean, it is sort of cute but difficult to implement.
Jack, sorry,
Yep.
There's a question in the chat. I think there's a typo on your slide. Can you just look at little GLM? You say can ensure that div of.
Yeah, it should be equal to 0. Thank you. Yeah.
Thank you.
So I should correct this, equal to 0. Thanks.
Yeah.
That is the whole point, really. Okay. All right. So this was all about the kinematics, really, right? I've been just talking about how to best define the average to have a nice scalar equation, for instance. What about the dynamics? The claim would be that the momentum equation, for instance, takes a simpler form if you do a Lagrangian average rather than an Eulerian average. So when you do Eulerian average, you get those Reynolds stress terms. What is happening when you do Lagrangian average? Well, you get something which is substantially simpler, and it preserves the structure of the original equations. So this has a long history going back to Eckhart, for instance. There's very nice work by Brotherton. And then the kind of standard for the field are two papers by Andrews and McIntyre in 1978. And then I recommend the book by Oliver Bühler, which gives a nice summary of this theory. So because Lagrangian averaging builds in advection, it's going to preserve the fact that the equations for fluids typically have a nice advective structure. In particular, properties which are materially conserved are going to be also conserved after averaging, right? So vorticity is conserved as a vector field, for instance. Once you pass it through this machinery of Lagrangian averaging, the Lagrangian mean velocity will be conserved as a vector field. Similarly, for potential vorticity, for those who are familiar with the idea, is going to be conserved as a scalar field. And so the claim is that Reynolds stress terms and similar terms will be minimized in the average equation. Now, I'm kind of conscious that the theory is not super popular, hence this talk, I guess. One of the reasons is probably that the theory seems a bit complicated. And if you go in the kind of classical paper by Andrews and McIntyre, it's true that if you look at the kind of main result, really, which I'll explain in more details, it looks pretty difficult to take in. And the way to get there also is quite complicated. Another point is that there are very few numerical computations of this Lagrangian mean. And pretty much all that's been done so far has been to use it in a perturbative sense. So where you have something like a dominant mean field and then small amplitude perturbations, and you can do amplitude expansions. and say something useful. This is how you get to concepts like Stokes drift, for instance, which are used very widely. But this is restricted to small amplitude perturbations when, I guess, the main point of Andrews and McIntyre is that they have a finite amplitude theory. So it'd be nice to see it applied in a finite amplitude context. Okay, so what I want to do now is to explain that, in fact, if you look at this problem in the right way, then everything is fairly straightforward. And the right way is to think a bit more geometrically about the equations governing fluid dynamics. So I'm going to do everything at the level of the early equation for inviscid incompressible fluids. I have to confess that viscosity is a bit of a problem for those theories, but I'm focusing really on high Reynolds number flows, where we can certainly in the first instance ignore viscosity. Okay, so this is the usual form of the Euler equation, right? So material derivative, as we call it, of u is equal to gradient of pressure, and then the constraint of divergence-free velocity field. Now, one thing to observe is that this d by dt plus u dot grad is a material derivative, but really of scalar fields, right? It's not a material derivative of vector fields. And we know this because when we write an equation for the vorticity vector, for instance, we encounter the proper material derivative of vector fields, right? Something like u dot grad vorticity minus vorticity dot grad u. Right? This is not what we have here. We have simply u dot grad u. So there's something a bit amiss in this usual formulation. So the first thing I'm going to do is to rewrite the equation by adding this gradient term here and then compensating on the right-hand side. And this form is really a form we are familiar with, because if we multiply it by dx, okay, little line element, then the right-hand side turns out to be the material derivative of this u dx. The left-hand side, sorry. And the right-hand side is an exact gradient or an exact differential, right? So this pi is this pressure minus velocity square over 2. Okay, so this is really what we do when we derive Kelvin circulation theorem, as for instance done in Bachelor's book. Okay, so once you have this, you integrate over a contour, which moves with the flow, and you conclude that this should be equal to 0, another typo. Maybe I can remove the, so the constant is 0 here, right? So circulation is conserved. Okay, so the geometric viewpoint I want to take is to think of this u dot dx, so this integrand of Kelvin circulation theorem, as really an object in itself, okay, not the dot product of a velocity vector with this dx, which is a bit mysterious. Okay, so we're going to think of this u dot dx as the kind of an object in itself. I call it nu. And what is it? Well, it's a momentum, okay, it's a u, density is 1 here, and it's a one form, right? So objects of this type are really the kind of dual of vectors. So these are the objects which you pair with vectors to get a number. They are the covariant vectors or the covectors, right? So it's equivalent to a vector simply in the dual basis. So in Rn, for instance, the components of this vector, of this momentum one form, are going to be identical to the components of the velocity. Simply the one form carries with it the one form basis in the same way as vectors carry with them the basis of vectors, right? And the two bases, those dx and the usual basis ijk, are dual bases. Okay, so this is what's happening in Euclidean space. In general, what you have is that the momentum one form is related to the velocity vector via the metric, right? So you use the metric to lower indices, if you like. So this is the coordinate formulation where you have the vector here with an upper index. There's a metric which is a tensor with two lower indices, and then you do the summation here, which is implied to get the momentum. So at this level, momentum and velocity are really the same thing, except expressed as different objects, right? Now the beauty is that the Euler equation as written here is in fact a formulation of the Euler equation in terms of this momentum one form. Okay, so if I write a bit more geometrically, it will take this form here, okay, where we have a proper derivative here, material derivative, which is the Lie derivative. And then you can just look in your favorite book to find what is the expression for the Lie derivative of one form in components is given by this, which is precisely those two terms which were in my formulation of the Euler equation. Okay, so, well, first I think this question is pretty, and second is going to be very useful for Lagrangian averaging. Okay, and the velocity vector is also divergence-free. So why is it useful? Because now we have a proper material derivative, a Lie derivative, and that behaves very well under flow maps of various kinds. And this is what I need for Lagrangian averaging. Okay, so just to remind you, the whole business here is to take the flow map, split it into a mean map, and then compose this with a perturbation. What I want to now do is to do some kind of meaningful Lagrangian averaging of the momentum equation. So I start with the momentum equation written in this kind of geometric way. And then I think a bit about what's happening here. Okay, so we have this labeled space. We have those various flow maps, right, telling us where a particle is in several realizations of an ensemble. There's a velocity for each of those realizations. It makes no sense really to average the velocity in this fluid domain, right, because the velocity of the same particle is actually located in a different tangent plane, right, because the particle in each realization end up in different positions. If the geometry is a bit interesting, different positions mean that the tangent planes are different and not easily to relate, right? So this is why if you have flow on a sphere, for instance, if you start averaging velocities at different positions in the sphere, you get something which is not tangent to the sphere. So we need to somehow bring this back to the mean configuration to do the averaging. And it turns out there is only one meaningful way of doing this. Okay, so there is this perturbation map linking the mean position to the actual position. There's only one meaningful way of bringing back the information from the fluid domain to the mean position is using what's called the pullback by this map. Okay, so the pullback operator is just like a change of coordinates, right? It's really going from a basis in this fluid domain to the kind of natural basis, which is the pre-image by this psi. Okay, so what I'm going to do is to take this momentum equation, pull it back. Okay, the details are really unimportant. What it means, I'll show this in a second, and then average. Now everything is meaningful because I'm averaging velocities which have all been brought to the same position. Okay, so this is a kind of sound thing to do. Now, because I have this nice Lie derivative here, there's a very simple commutation relation, so you can pass this pullback under the Lie derivative, and the price, which is in fact a reward that you get, is that the velocity is turned into the mean velocity. Okay, so the summary is that here is the Lagrangian mean momentum equation. It's very simple. It just says that the Lagrangian mean momentum is going to be advected by the Lagrangian mean velocity up to the divergence, or up to, I should say rather, a differential, which is like a gradient, right? And the Lagrangian mean momentum has a simple expression, right? It's just the momentum in each realization pulled back averaged. And if you unpack it in coordinates, you get this. So you get, this is the momentum. So here x is the mean position, so this is the displaced position, times this Jacobian, which is just the kind of, this is a matrix you have to multiply to get something which is geometrically meaningful, right? This is a change of coordinate matrix. So everything makes sense, it's fairly straightforward, and then this equation which I write in this term turns out to be equivalent to Andrews and McIntyre equation here, okay? And then what looks pretty mysterious, I think, in the original formulation are terms like these, okay, where you have what looks like indices at the wrong place, really. The reason they appear in this way is because what you really have is a one form, not a vector. And so indices should be downstairs, and hence you get a gradient, okay? So this term here, the material derivative and this term here combine in this Lie derivative. Okay, so the summary is that, as hoped, the Lagrangian averaging has preserved the structure of the Euler equation. This equation looks very much like the original one, okay? The only difference is that in the original equation, the momentum here is advected by a velocity which is just essentially itself related by the metric, right? So there are two sides of the same object. Now this link has been broken. The momentum here is advected by the mean velocity, but they are not related in a simple way. Okay, so it's not the case that I can get straight away from mean velocity to mean momentum, because the perturbation have a dynamical effect. This dynamical effect is completely encoded in this difference between the mean momentum and this mean velocity turned into one form using the metric. Okay, that's what's called the pseudo momentum. Okay, which is what shows up here. Okay, so the idea here is that the equations have a very simple structure. All the effects of the fluctuations are encoded in this pseudo momentum, which is the kind of lack of simplicity, the lack of the fact that we've lost the simple connection between the mean velocity and the Lagrangian mean momentum. This structure carries over to to more complicated problems, and every time what you have to do to define a Lagrangian mean of anything is to take this anything, pull it back by the perturbation map and average. And then what the pullback means depends on which object you're considering. Okay, so you can do this for scalar, in which case it's just a composition. You can do it for vectors, or maybe for two forms for magnetic field. You can do it for things like stress tensor. And every time you get nice Lagrangian mean equations with a relevant version of the Lie derivative. And then one key point which explains my odd notation is that the Lagrangian mean velocity is not the Lagrangian mean in that sense. Okay, so I've defined it as being the velocity associated with the mean map, which is my fundamental object. It differs from what you get by taking the velocity, pulling it back and averaging. Okay, there's no link between the two, which is a source of confusion. And now if we want to do some modeling, what we have to do is to somehow represent this P, right, which is the effect of the fluctuations in terms of the mean fields. Okay, so we need some kind of closure, which is really the ultimate aim of those theories. Okay, so now I want to shift gear. I've done the formulation part, and I want to speak about the computation part. So if we want to start doing some closure, for instance, we should really be able to diagnose Lagrangian mean fields to see how they evolve, to calculate pseudo-momentum fields, and try to relate the two. Okay, and this is something which has been lacking so far, is a way of, say, from a simulation, compute Lagrangian mean without too much problems. Okay, and so this is something which I think we've made progress on. I'm going to now focus on temporal means. Okay, so I'm going to really think about two timescale systems and how we can average over the fast timescale to say something about the slow part of the flow. And I'm going to focus on this fairly large class of means, which is that if you have a function of time only, you just convolve it with some kernel, okay, to get the mean at time t. So I've just shifted from an ensemble mean to a time mean, but that's okay. These are the ones we're going to use in practice. Okay, so people have been computing Lagrangian means. For instance, there's a nice paper and a software going with it by Callum Shakespeare and others, following what I would call the traditional method, which is, this is Lagrangian, so surely you have to put particles in your flow. So you seed particles in the flow, large number of particles, you collect statistics, so you follow fields along trajectories, and then you average those. Right? That's quite costly to put particles in. It has problems of things like a clustering of particles. It's also inconvenient. You have a nice code which, say uses finite differences. You now have to write another part which deals with particles. Wouldn't it be nice to have something which is entirely PD based? Okay, so there's something which Hossein Kafiabad proposed, and which I've kind of helped him extend. The idea here is that we're going to write down PDEs, so partial differential equations, satisfied by the Lagrangian mean, and solve those using the usual scheme that we use for our simulations. Okay, and ideally you want to be able to solve this on the fly, right? So as we solve the dynamical equations, we want to be able to diagnose at the same time the Lagrangian mean field, and we are able to do this. So okay, so I'll explain this in terms of a very simple mean, and Oliver Bühler is to be thanked for suggesting using this mean, which is the exponential mean. Okay, so if you have a function of time only, the exponential mean corresponds to this exponential kernel. So it's exponential with a heavy side, if you like, in that the integral here is chopped at time t. So the beauty of this is that it's causal, right? So to know the mean at any given time, I only need to know the signal in the past. It depends only on one parameter, this alpha. That's an inverse time scale. So small alpha will mean that you average over a long time. And then you smooth things out, right, by averaging over the past from time t equals 0 to, in principle, minus infinity. The advantage of this exponential mean is that you can also write down an ODE for it, for a function of time only. This is the ODE, right? So this is telling you that the mean is simply sort of relaxing to the actual value with a relaxation rate, which is this alpha. Okay, that's very nice because for us, we'll be able to write PDEs mimicking this ODE. Okay, so once I've decided of my mean, my averaging operator, I can apply it to the flow map to get the mean flow map. Okay, so I'm going to use here this GLM version where I'm not worried too much about the geometry. I'm going to just average the flow map component-wise. So I take component I of the flow map, I fix my particle label, and I'm applying this exponential mean to get the mean map for this component. Okay, of course, we want to avoid computing this map, and we can do this. All we will need to compute is the perturbation map, this psi map. Okay, so what do we do? So first, we need to know something about the mean velocity. Well, it's just a time derivative of this, right? So you can just take the time derivative of this operator. There'll be two terms, one coming from the t here and one coming from the t there. It turns out, with a bit of calculation, that you can write this mean velocity as alpha, so that's my filtering parameter, times the perturbation map minus the identity, if you like. Okay, so I should say maybe u of x. Okay, so there's a simple relationship between the perturbation map and the Lagrangian mean map. So I don't know yet what the perturbation map is, but that's fairly easy to find out, because what I know is that the full flow map, so that's the one whose velocity is u, is known, is going to be this composition, right? So if you take this, you time differentiate, you use the chain rule, you get to this expression, which is an equation for the perturbation map itself. Okay, so we now have a closed system which allows us to find, given the velocity field, to find the perturbation map and find the mean velocity, and both are coupled, right? So the perturbation map is advected by the mean map. Okay, so it's a simple, well, simple. It's a PDE, right, which you can just go and solve on a computer. It's an advective type of PDE, not surprisingly. It's really the PDE version of solving for particle motion, right? And here comes about what is also familiar if you solve for particle, which is that you have to interpolate the velocity field, right? So this is a bit maybe sometimes complicated to implement. There's an interpolation step. Now, if you want to calculate the Lagrangian mean velocity of anything, so let's say a scalar, you also have a PDE to solve. Okay, so here it is. So we have advection by this mean velocity, and then we have this relaxation of the Lagrangian mean to the field itself at the displaced position. Okay, so this is really the PDE version of this ODE formulation of this exponential mean. We have a very similar term here where, again, there's interpolation involved. Okay, so we've been implementing this in a very simple context so far. I mean, we're hoping to do more. The context is just a shallow water model. So shallow water is just a shallow layer of fluid, so shallow that you can assume that the fields are depth independent. So there's a velocity field which depends only on x and y, not on z. There's a height field which depends also on x and y. You have to you have to solve the momentum equation and then a continuity equation for this height. And because I'm interested in geophysical applications, my shallow water is also rotating. Okay, so dynamics of shallow water is interesting because it combines vertical dynamics, so eddies and that kind of things, with waves, which are just Poincare waves, which correspond to surface waves, right, in the shallow layer. So what we're going to do is to see whether our method can be useful at filtering a Poincaré wave, in fact a single Poincaré wave, in an interesting simulation with turbulence. The setup is completely straightforward. We have a doubly periodic domain. We've used spectralization both for the dynamical equation and for the Lagrangian mean equation. And we pick this parameter alpha to filter out the wave. So it's a time scale which is, the wave is fast compared to the flow scale. We pick the time scale of averaging between the wave time scale and the flow time scale. Okay, I'm going to show you a little animation. So the top row here is going to show the vertical vorticity. It's the only vorticity in this model as a function of x and y. So just here at the initial time, you see this combination of a mode 1 wave, right? You see a crest and a trough here. It's going to propagate to the right. And then underneath this, at a similar amplitude, in fact, a small amplitude here, you can see some kind of interesting vortices. Okay, they're a bit dimmed because of the large amplitude of the wave, which is dominant. I'm going to run this, and then I'm going to compare the Lagrangian mean vorticity here with the Eulerian mean vorticity. Okay, and at this level, I mean, it's just going to be observing the pictures and then concluding that we like the Lagrangian mean picture better. Okay, so here is the evolution. So after a little transient, while the mean settles, what you can see here is that the wave is pretty much very well filtered in both the Lagrangian mean and the Eulerian mean field. You can still see some kind of blinking, right? So there's still some remnant of the wave, but now the vortices are very well visible. Okay, and they evolve at the time scale. There's not much evolution going on. We could run this for longer. But the main point, I guess, here is that the Eulerian average has blurred the picture considerably, right? And the reason is that all those vortices are wobbling as a result of the wave dynamics. And so the average at fixed position is taking in several values of the vorticity in this case, averaging over that and blurring the contour of those vortices, right? So if at a very simple level of kind of image analysis, if you like some tool to diagnose vortices from a flow which is kind of disrupted by fast perturbation, the Lagrangian mean gives you something quite nice, right? And then the other panel here is showing the potential vorticity. So potential vorticity, which is vorticity over the height of the shallow water, has two virtues. One is that it's conserved materially, so its evolution is just advection by the flow. And the other virtue is that Poincaré waves have no signature, at least at a linear level, on the potential vorticity. Okay, so that's why when you see the field here, time t equals 0, you don't see very much well, you don't see at all actually the signature of the wave. You're going to see it in the animation because it's participating in the advection of the advection of the potential vorticity, right? So the waves, are going to make the vortices wobble, right? And the effect of this is that when we look at the Eulerian mean, right, we get again a very blurred picture, whereas when we look at the Lagrangian mean, we have all those detailed filaments and what looks like what the evolution of the vortices should be, right? So you get thinning of filaments and so on, which is completely has disappeared in this Eulerian mean picture. Okay, so this is all solved fairly straightforwardly by adding an equation for this map psi. So it's in fact two PDEs and then a PDE for the Lagrangian mean field, the Lagrangian mean scalar. Now, in my Lagrangian mean field, we could see a bit of trace of the oscillation still, right? That's because the exponential filter is a pretty low-tech filter. And one way to see this is using a Hofmöller diagram. So this is time and y. I fixed the x value, so I'm just looking at a kind of column in my fluid, and I'm looking at the vorticity, and you see this kind of corrugation here, okay, which is a sign of the wave, right? And it's very fast propagation of waves in this direction. So this is what I obtained with my my exponential filter. Now we can try to do better and improve the filters, and we've done this in two ways. One way is by using a filter which consists, instead of a single exponential, in a sum of exponentials. So this is the kernel, the convolutional kernel used for filtering, right? So this is the one for the exponential filter with this heavy side. You can replace this with a sum of exponentials still with a heavy side, so that remains causal. And then everything is pretty much, as I explained, for the exponential filter, except that you have to solve several PDEs. There's a kind of hierarchy of PDEs, right? So instead of having just one, maybe I can show this again for the ODE here. Instead of having, if you have just a function of time, instead of having one ODE, you have a system of n ODEs corresponding to the n terms that you put in your sum of exponentials. So similarly here, you have n PDEs to solve. It turns out that just adding one exponential, so having two exponential terms here, does a very good job for the prime we've looked at. Okay, so this is the second picture here, is using this kind of second order filter. It's a Butterworth filter, which is the kind of best filter in some sense that you can get in this class of filters. And you can see hopefully that the corrugation here has disappeared, right? So there's essentially no trace left of the wave. Now all that we see is the kind of slow evolution. So that's something which my PhD student Abhijit Mins has been doing, and then Lois Baker has been working on something more complicated and more general, which is abandon this idea that the filters have to be causal, so that they should depend only on the history of the signal, and then solve the problem for arbitrary kernels here. Okay, so this is getting more complicated because every time you want to average fields, you have to solve PDEs in a full domain centered on the time at which you want the average. Okay, and it's centered and has a length which really should be all the way from minus infinity to plus infinity, but you truncate somehow, right? So every time you want a new average, you calculate it afresh, whereas for the previous approach, you built on the previous knowledge, right? It's kind of a Markovianity in the causal filters, which has disappeared here. The beauty of this approach is that you can select your favorite filter. So for instance, Lois has been using this this low-pass filter which you really truncate in the frequency domain. So this is the frequency, the Fourier transform of the kernel, and you just chop off all the frequencies larger than some threshold, right? So this is a kind of and she's been using more sophisticated filters, like high-order Butterworth filters, for instance. And then you get very nice pictures. So here, let me just focus for the moment on the vorticity field in a very similar setup. You get the Lagrangian mean vorticity here. Okay, so we're going to animate this, and so it's moving very nicely, right? No traces of the waves. Okay, and then the other panels here are showing two things. This panel here shows something which is very often done, which is to calculate Lagrangian mean typically with particles, and then referring the field not to some Lagrangian mean position, but to the final position of the particle, so the current position of the particle, okay, which is written here. So this field zeta star is the vorticity at the current position of the particle, not at its mean position. And if you do this shows it nicely. You still get quite a bit of oscillation in the field, right? So this field is average in some sense, but it's still being advected by a moving, by the wave in this instance. And then this final panel here shows the kind of reconstruction of the wave, which is my last point, which is that once you've computed Lagrangian mean, you may want to calculate the perturbation, right? So by subtracting the mean in some way. So this is something which we're familiar with in the with Eulerian means, right? So when you have the Eulerian mean, you take the full field, you subtract, and you call this the perturbation, and you look at it and hope that it's simple enough. You can do something similar with Lagrangian means. The natural thing to do is to take the Lagrangian mean at a given mean position and look at the field not at the mean position, but at the position where the particle really is. Okay, so this is the position of the particle whose mean position is x. Okay, so this makes more sense. So that defines the field. our approach tells us what this mapping is, so we can do this calculation. And here's the result, right? So the top panel here shows the Eulerian mean vorticity, the perturbation, sorry. So what you get by removing the Eulerian mean. And you see something which, okay, is dominated by the wave, but has still a kind of strong signature of the flow underneath. When you do this the Lagrangian way, you get something which looks like a pure plane wave, right? So this is something which, well, looks quasi-miraculous. I still have to maybe figure out why this works so well. But there is a sense in which, in this Lagrangian frame, the wave field is now really a pure plane wave field, right? So the bulk of the nonlinearity, which is advection, has been removed. Okay, so this brings me to my conclusions. So my aim was to show that Lagrangian averaging was fun. I'm not too sure I've succeeded in that, and useful. Maybe I've not succeeded in that either. Okay. Taking a geometric viewpoint, I think, helps understanding what's going on. So there's a bit of a price to pay in terms of thinking of one forms at the same time as vectors. But the reward is that all the operations involved in taking Lagrangian means become very natural and straightforward to understand. In particular, you can think about Lagrangian averaging any tensor, and systematically you're going to get pretty equation for the Lagrangian mean. And I guess the main message here is that in this formulation, what you find is that all the effect of the fluctuations is captured by the absolute momentum, which is here nicely defined, right, as the difference between the Lagrangian mean momentum and the Lagrangian mean velocity turned into one form. And then the second part of the talk was about the fact that we now have what we think are kind of efficient methods to calculate Lagrangian mean from simulation. With that, the next steps will be to actually use this to diagnose the absolute momentum to try to start doing parameterization in a Lagrangian mean setup. Okay, that's the end of my talk.